Well, thank you, Amanda, and thank you, Karen. Good morning, everybody. So I will be, as Amanda just said, talking about some of the technical requirements. I'm really going to focus here on the hardware, and in particular, some of the lessons that we learned from Argus 16. And so really this talk is coming from the whole Argus hardware team, as I've listed here. And of course, there are many more people involved, both at JPL, at Caltech, and at Green Bank than I've listed here. So what I will do here is give a brief introduction, first just to motivate why we're interested in focal plane arrays and what they are, what their peculiarities are. And then, as I said, move on from the technical lessons that we've learned from Argus 16. But I do have to say, you know, there were tremendous amount of work done before, especially by Neil Erickson and other groups. And so we've learned a lot of lessons from them as well. So I'll focus really on the optics, some of the layout questions, a little bit about the microwave electronics and the cryogenics. But as I go through this very quick overview of what's involved in building an array receiver, I think the real thing to focus on here is looking at the need for simplicity, the advantages of integration, a tremendous need for manufacturability and reliability for such complex systems. So those are really the themes, even as I cruise through kind of a high-level description of some of the things that we've done for Argus 16. So I'd like to start just with a little motivation, and this comes in part from the title of the conference or the workshop, which is this is the wider part of the discussion. And the reason that we really want to be able to use focal plane arrays effectively is because of context, astronomical context. So I have here an image over on the left of the integrated intensity toward the galaxy IC342. And you can see this is a large field map. This is about 4 by 6.5 or 7 arc minutes. The beam, as we just heard, at 115 gigahertz, this is 12 CO, 1 to 0, is about 6 arc seconds. And so that means there are about 3,000 pixel elements across this image. So the fantastic thing about single dish telescopes and arrays is the very high sensitivity to extended emission. So this is a real complement to interferometers, where the interferometers are very good at mapping small areas in exquisite detail, but lose the very large spatial frequencies. And so what we're doing here is we're putting things from the interferometers into context, or adding the short spacings to interferometer-driven maps to make hybrid maps. What we're doing with spectroscopy, of course, is looking at kinematics and dynamics, and that's highlighted over on the right. So with a radio focal plane array, we're not just getting the integrated intensity maps, but we're also getting velocity fields. And you can see the velocity field of IC342 shifting from red to blue as we see a little bit of the galaxy's rotation. Of course, we're also measuring physical conditions through different lines, abundances by looking at the intensity of different species, and many other things. So this is not just imaging, but also spectroscopy. And this is one of the main differences between focal plane arrays in the optical and in the radio. So we're used to having our cell phones with megapixel CCDs. And so then the question comes, why should we get excited about a 144 pixel array? And the answer to that is because we're getting the spectroscopy as well. So the challenge to this, the problem with this, is that each one of the pixels, there's a drawing of Argus over on the right, a CAD drawing of it. Each one of the pixels is a complete radio spectrometer. And so while you might look at the CCD on the left and say, well, that's, you know, a few megapixels, the problem in replication for a radio receiver is that it's not simply replicating a pixel with photolithography, but replicating an entire receiver chain. And this is really what drives the need for simplicity, manufacturability, integration, and so on. There are many parts that all have to work well together. Another big difference between an optical focal plane array, like a CCD, and a radio one is that we have to worry much more about diffraction. So a typical pixel in a CCD is about 20 or 50 wavelengths across. In a radio receiver, of course, we're in single mode optics, and so a single pixel is actually pretty big. And there's a very straightforward way to make an estimate of the size of the pixels here, and that also then drives the minimum size of the modules that one needs to make. So taking the standard theta equals lambda over d approximately, and also doing a little geometry for a thin lens, you quickly come to this expression toward the bottom, so that the spacing between feeds has to be something of the order 2 times f over d for the effective focal length and diameter of the telescope times the wavelength. So at lambda equals 3 millimeters, so in the millimeter wave band where we're thinking of Argus 144, and for a f over d ratio of about 2, which is about what would correct for the Green Bank telescope at the secondary focus, this means that the pixels must be spaced by about 12 millimeters, driven by the need to space them by about two focal spots to keep the diffraction losses down. And so this also drives the minimum module size. In fact, for Argus, we wound up with a somewhat larger horn. You can see here's an image from Patty Voll's thesis of the Argus horn, and you can see that the horn itself is about twice the minimum spacing. The reason for that was partly because we wanted to have a very simple horn that was easy to machine. These were made in the machine shop at Green Bank. You can see it's a smooth ball horn, which is much easier to make than a corrugated horn. And this is an important consideration for thinking about building a very large array, as how to best make all of the horns. So that gives us about 4 pixel spacing, 4 lambda over d spacing, and that's given here by the red spacings in this drawing from Matt C's thesis. So the red shows here the Argus 16 array, and the blue shows the Argus 144, still in the same 24-inch turret port. So things still fit quite well. This is a good thing because, as Roger Norad and Shrikant figured out over 20 years ago now, anticipating all of this, the field of view is actually reasonable as long as you don't go too far away from the axis. So this is Green Bank Memo 199 from 1999. And I've picked here one of the figures that they have. This is at 90 gigahertz, about 33 centimeters, about halfway across the port in the worst direction. The telescope's not symmetric, so the aberrations are not symmetric. But you can see even 13 inches off from the center, the first side lobe is still down by a little bit more than 10 dB in the elevation plane, and even better in the cross elevation plane. So this is still quite reasonable as long as we don't go too much larger than this size. You noticed probably that the layout was rectangular. It was not a set of beautiful concentric circles or something, or a hexagonal pattern. And the reason for that was simply practicality. Again, it's important to be able to integrate things easily. And so we built a set of 4 sets of 4 each linear arrays and stacked them up. And this made integration very simple because, in addition to having the modules that we will talk about in just a moment, the receiver modules themselves, we're able to simply snap them into carriers that carry banks of receiver modules. And you can see this a little bit more clearly probably on the image on the right-hand side, where you see 4 of these modules stacked up. And this makes integrating the system quite a lot simpler, with a carrier board for the microwave post-processing, and bringing in the DC bias and taking out the IF, bringing in the LO, and being able to fan that out easily on a printed circuit board. So a rectangular layout is simple. It provides pretty good sky coverage. Argus 16 has no field rotation, as some arrays do. The sky rotates some during the map. And I think Eric Rosolowski may well talk about some of these aspects in a talk on Thursday. So really one of the key things in building Argus 16 was making the highly integrated front-end modules. This is a complicated receiver, and as those of us who build things know, connectors are usually the biggest problem anywhere. So eliminating connectors, minimizing distances, all of these things are good. So this was a extension of work that had gone on at Caltech and JPL, which includes 2 stages of mimic amplifiers, filtering, more amplification, and then a double balanced mixer, or excuse me, a sideband separating mixer, I and Q mixer with the harmonic mixer, second harmonic mixer. And this whole module is quite compact, and it then snaps into the board that I just mentioned, bringing both the IF out and the LO in, as well as a DC connector that brings the bias for all of these in. One thing I would suggest for Argus 144 is simplifying the way we bias things. We can talk about that a little later. Cryogenics, that's a big deal. It's a large array. I again show Matt's image over here on the left to remind you that Argus 144 will be 9 times larger than Argus 16. And although it's a terrible idea to show tables in talks, I'm showing a table here that's ordered in, these are the cryogenic heat lifts that were required within Argus 16. And you can probably guess that to get to Argus 144, I'm going to multiply by 9, which is this slide. So this doesn't really show what exactly will be needed. It's going to be very difficult to come up with 90 watts of heat lift at 77K, for instance. We'll have to do better than that. IF cabling will also be able to improve. But the point here is I've highlighted in red the areas that are going to take more engineering than we needed to do for Argus 16, be much more straightforward. So we can gain a factor of a few. We had heat lift to waste. We had heat lift to spare for Argus 16, but this is going to be a major area, the thermal design, as we move forward. Other groups have dealt with this. We may well need to think of warm horns with thermal breaks and a cold LNA block. There are also potential choices for materials on IF cabling. As I said, we could be pretty wasteful in some of our cabling. And you can see that from the ratios of heat lift at the 2 different stages.
So just
one final problem I want to mention.
3 minutes.
Perfect, thanks. One final problem I want to mention is bringing out the IF. This was something we spent a certain amount of time on. For Argus 16, we tried a fairly novel technique of using microstrip line in arrays of microstrip line to come out of the cryostat. And over on the left, you can see an image of that with 8 separate microstrip lines here on 2 ground planes. This was a test setup. And then bringing a line in from here and coming out here rather than having an individual coax cable running through the whole cryostat. Bringing the IF out of the wall of the cryostat is another problem, and that we dealt with by, again, just bringing this end up and splitting it into separate outputs that were in an array of SMA connectors. This view here is from the outside of the cryostat, here looking from the inside. So this is another problem. For Argus 16, we wound up bringing out 32 IF signals. We had an IQ mixer. For Argus 144, this is going to be a really staggering problem, bringing out either 144 IFs, or if we come out dual in a sideband separating mixer, 288 IFs. So this is going to require considerable thought about bringing things out. Microstrip line arrays, Matt Morgan has also spent some time working on these for similar reasons. But we need to think about whether this is a good approach. They're somewhat fragile, or whether we go back to brute force individual semi-rigid coax lines, or one particularly elegant solution would be to have fiber transmitters inside the cryostat, bringing things out directly to fiber. So I want to conclude just with a brief list of some of the choices and challenges that we're going to need to make, generally interrelated. And so it's very hard to separate them into different subsections. This is another key point. In addition to simplicity and integration, the system really has to be considered as a whole to work out. It's a very complex system that has to fit in very compact mechanical, electrical, and thermal environment. So I'll leave you with this list at this point, and we can have some, for people who are particularly interested, we can have some more detailed discussion in a session a little bit later on today. And with that, I thank you for your attention.
Thank you so much, Andy. We have a couple of questions already, but I just want to remind people that you can use the Q&A to ask your question. You can ask anonymously, but also I will not read names of the questions, so you will remain anonymous on the recording. The first question we have is, I understand that the IF bandwidth is relatively small, 1.5 gigahertz or so. If so, what is the main limiting factor to increase that bandwidth?
Well, for Argus 16, we had the constraint from the spectrometer. And so there was now a point in going to a much wider bandwidth. The limiting factor to that would basically be in Argus 16 is essentially in the first down conversion mixer bandwidth and the components that we used for sideband separation. So neither of those were fundamental. We didn't press on either one of them because there was very little point in doing that. There was no way to analyze that bandwidth. But it's all just straight engineering problems. There's nothing fundamental going on here.
Thank you. We have a second question that what's the cryogenic temperature at which the entire system is maintained?
Oh, okay. Yeah, the array runs at about 20 Kelvin. And then there's a second stage with cooled IF amplifiers that runs at about 75, 80 Kelvin. And then we come out to room temperature. So it's the standard Gifford-McMahon refrigerator temperatures, about 20, about 77, and then room temperature. We run a little bit colder because our heat loads are below the maximum loads that the refrigerator is rated for. But there's no particularly strong temperature dependence to anything.
Thank you, Andy. We have time for a couple more questions. I just wanted to ask, in your talk, you did a great job of outlining sort of some of the challenges of creating an Argus 144. What do you think is the biggest thing we should be worrying about?
Quite possibly the cryogenics, in the sense that many things feed into that. So there's the radiation load is one. There's the power dissipation from 9 times as many modules. Modules dissipate very little power, fortunately. The mimics need little power. The second IF may require much more in the way of power. That was another fairly power-hungry place that requires cooling. Miko's talk, I think, will address that one. And probably just there's just conduction problems of having 144 or 288 cables coming out carrying the IF, and that is a big problem. The other main problem, I would say, is integration and keeping things compact. The Argus electronics, we can look at them a little bit later in a discussion section, but they kind of grew, and they are actually much larger physically than we'd expected initially. So that's another area to keep an eye on. So I think those are the main areas. Otherwise, the noise temperatures that we need, the really hard things I think are done. It's really getting the engineering to make the system a system that's going to be the main problem.
Thank you, Andy. I'm going to take one chair's prerogative and ask one more question from the Q&A because I'm interested in knowing the answer. Would you consider using a lens/feed configuration for the optics to more densely integrate the pixels in the array?
You can do that. The problem is the integrated receiver modules can't be terribly tiny. So one could do that. And Quarry or Sequoia has actually made smaller modules, but not with as much going on in them. But the modules that we have for August 16 are about 1 inch on the side. It's harder to shrink them down by a whole lot more. And so the lens horn configuration could be very useful for thermal control, however. The lenses still have to be about the size, well, the lenses still have to be about this, have to be the size of of the current horns, or maybe somewhat smaller. The other thing that Neil Erickson has done for his receivers is to cut the sides of the horns into squares, and made square horns, and that brings things smaller more quickly than probably a lens would.
Thank you, Andy. Lots of food for thought. We're going to have a discussion at the end of the day at noon Eastern with Andy about these and other issues. A lot of great questions in the Q&A that unfortunately we didn't have time to get to, but Andy can type out answers after his talk. So hopefully you will not be bereft.
And I will be reading them so that we can take those on in the discussion.
Excellent.